Welcome to the Consulting Specifying Engineer webcast, Microgrids 301, tying multiple power systems together with intelligent controls, sponsored by MTU On-Site Energy. I'm your moderator, Jack Smith, and I'm happy to join you today on behalf of Consulting Specifying Engineer and CFE Media. Here are some tips to help you get the most from today's webcast. If you're experiencing issues with your slides or audio, refresh your browser or click the Refresh Media button directly under the presenter's picture. You can control the volume of this webcast by adjusting the volume on your computer or by adjusting the...
I think, did Greg give me this one? He was telling me
by adjusting the volume on the webcast platform. If you are having technical problems with the audio or a slide presentation, click on the question mark at the top right corner of your screen to access a list of system checks to try before contacting an online technician. But if you do need a technician, type a message in the Ask a Question box and someone will get to you as quickly as possible. Individual technical questions will be answered in the Answered Questions box. Type questions for our speakers in the Ask a Question box on the left side of your screen. The live Q&A session will begin after the presentation concludes. Today's webcast is being recorded, and you will receive an email within a week with a link to the on-demand event. To download a certificate of completion and a PDF copy of the presentation, use the Event Resources tab on the left side of your screen. Those documents will also be available with the on-demand version of the webcast. Now we will hear from the sponsor of today's event, MTU On-Site Energy. At the conclusion of the video, you may experience a few seconds of silence to compensate for varied internet speeds. Please stay tuned after the video for today's presentation. I'm happy to introduce today's distinguished presenters, Christian Mueller and Tom Drake. Christian Mueller is a senior sales engineer at MTU Onsite Energy, who is responsible for engineering and sales support for the MTU Gas Power Systems product line in North America for CHP, biogas, and continuous power generation applications up to 2 megawatt. He has a degree in industrial engineering from the Technical University in Berlin, Germany. Christian brings 7 years of power generation experience to the company. Tom Drake is a regional sales manager for gas power systems at MTU Onsite Energy, where he handles continuous gas sales in North America. He earned a bachelor's degree in history and secondary education from Grove City College in Grove City, Pennsylvania, and has 12 years of experience in the power generation industry. Thank you for joining us today, gentlemen. The floor is all yours.
Yes, thank you, Jack. This is Christian Mueller again, and it's great to have you all here with us. So today I have also Tom Drake with me. Tom.
Good afternoon. Glad you could join. Everybody could join us today.
Yeah. So today is really the third part of our series on microgrids. And our agenda today is, again, a little refresher to begin with on microgrids. Then we're going to jump right into the controls, comparing genset master controls versus now microgrid controllers. We'll go into detail into the microgrid controller. And lastly, we'll talk about the software modeling based on a case study to kind of get an idea how we design and size these microgrids. So, Tom, let's kick this off. So for those people maybe who didn't participate in the first webinar on microgrids, maybe you can give us a little refresher on what a microgrid is.
So as we've talked about it in 101 and 201, really every grid, every microgrid is going to start with a load, some kind of electrical demand or thermal demand. And then, the focus really of our presentation has been, distributed generation resources, wind, solar, then specifically what MTU can offer is, different kinds of generation assets, diesel, natural gas, standby, and now, as we talked about in 201, we've got the energy storage portion. So that those distributed resources in different ways are going to support that load. And then what really the capstone and really what we're going to talk about today is how those systems and that intelligent system can control all of those assets and really work with the load as well as the utility grid. So that's really kind of a really brief summary of kind of what we've gone to and what we've talked about up to this point.
Yeah, so and now that we kind of, again, have a refresher on how it can look like, why would we maybe decide to use a microgrid?
So there's lots of different, reasons and different things that would be incentives to install a microgrid. Optimization, load management, and peak shaving, reduction in your environmental footprint. So really what you're talking about is an increased efficiency of the fuels and the resources that you're using on your site. Power security. You're seeing in the news more and more where the utilities are actually shutting off power ahead of time before they see events. So that resiliency can be really, of your facility, can be improved with a microgrid. And it really becomes a flexible solution. And then at the end of the day, also, it could be a money maker for your facility, whether it's offering grid services or really allowing you to purchase energy when it's the least expensive.
That's a bunch of good reasons there. So they all sound good on paper, but are there actually microgrids which are being installed or have been installed in the past?
Yeah, absolutely. As you can see by this graph, from 2014 up through 2020, you're really seeing an increase in the install base of microgrids year to year, with the biggest growth areas really being North America and the Asia Pacific regions. And really, along with that chart, you're seeing the reasons for microgrid installations growing are really a lot of those same reasons we talked about on the previous slide. Integration of renewables, interconnectivity with intelligent controls, and really you trying to be as self-sufficient with your own resources as possible.
Great. Could you maybe go into a little bit more the actual application where these become important as they kind of interact with the load and the grid?
Sure. So, we've talked about this before. So we're really, today in this last presentation, we're really going to try and tie in a lot of those things that we talked about previously. So what we look for are really two kind of main paths that microgrids are going to be installed. One is more of a grid support application where it's what we would call a utility-facing application, large scale or wholesale frequency and voltage support. And then our focus really is going to be more of a behind-the-meter application where we are supporting the customer. The assets are installed what we would call behind the actual meter, where you're going to purchase your generation from the utility and really manage your own use on your own site.
And I'm sure also part of that is the whole fact of renewables being integrated into the system and more renewables coming online.
This slide here is really a summary of like 3 or 4 slides from the last presentation. And what it really comes down to, like you said about the renewables, is it's with the increase of renewables on the grid really worldwide, we have to worry about the capacity factor of those assets. And the wind and solar capacity factors are below 35%. So we need the ability to have fast responding assets, whether it's reciprocating engines or grid storage devices that can match up to the low capacity factor of those assets to make sure that the power is always on when you're making your coffee in the morning, when you're watching the TV at night. So there's always power when it really kind of goes to the variable creation of power and the instantaneous demand. So now that we've kind of seen all those different, the different reasons why microgrids are important, so now we've talked about the different dispatchable assets, wind, solar, generation of natural gas and diesel. So now we're really going to get into the nuts and bolts of today's presentation, Christian. So we're going to talk about controllers. So the first kind of thing we're going to talk about is much more like a genset master controller. And how's that different than maybe some of the things we're going to talk about as we go into the presentation?
Yes, absolutely, and that's why I want to start off with the genset controller, and this is just a simple diagram showing, you might have multiple gensets, as you can see there, 1 and 2. You have obviously a master controller, which is going to dispatch these genset, and then the controls. So kind of a very typical genset application.
So when we look at that, so we're just really going to control each generator as a group, but just are we really matching those things up with anything?
Yeah, so typical master control functions obviously are, as we see here in this list, really it's a high-level controller interfacing to the individual genset controllers for a multi-unit installation. So it's really, controlling those different generators, having the start-stop sequence and the power set points on each of those gensets according to power or heat requirements if you have a CHP application. Obviously, we will want to load share between these gensets, maybe have some kind of a leveling of engine run hours across them so that they're all kind of at the same run hour. We will synchronize and control breakers through the master controller. There will be some kind of an island operation logic transitioning from grid parallel to island and back. Obviously, visualization like we see here where we see the breakers and the gensets, and typically today we also have remote access. So it's really just the control of those assets.
So, I came up in the power generation through diesel standby and standby applications. So this is really much more of a, power goes out and the generators are going to come on, and we're really going to control those generators within that network, kind of independently maybe from the grid in this kind of application, right?
Yes, absolutely. But it's really just the control of those generators. And when we
Okay.
look at a microgrid, as we can see here on this slide, it shows basically the same graphic. On the left is your genset application, but then on the right side, we have all these functions of a microgrid and these components. On the very bottom, that would be your battery storage system. Then you might have other storage, hydro storage. You might have renewables, solar, wind. So now that's where really tying all these resources together becomes a bit more complex.
Okay, excellent.
So if we look at just on a very high level, and I'll talk about these functions in a little bit more detail here, but just on a high level, what does a microgrid controller do? Well, it obviously will manage the complete microgrid. It will control the gas and or diesel generators, which typically we will have. There will be a solar, wind, battery storage, spinning reserves component to it. So all those additional resources we have there, and we will have to control all of these. It may or may not be grid parallel or island mode, can be both as well. Then really what differentiates a microgrid controller is that we're going to look at the optimization of these assets, both technically, that we use the right asset to produce the power we need, but also financially to always run the asset which basically produces power at the cheapest cost. So as all of these kind of microgrids are different, they also need to be scalable, these control systems. So it's really a more modular platform which allows integration of potentially even adding additional resources in the future, making it scalable, adaptable. Then visualization is also going to be a little more complex on this because we're obviously going to have multiple resources, and remote access will play a big role as well.
Okay, so now this really starts to make sense for me now. So when the generator kind of control, we're really it's much more of a technical control of the generation assets. But I think the one thing that you really emphasized here, or didn't maybe emphasize enough as we go forward, it's really the financial optimization of these assets, and that's really going to become important in the microgrid, where a standby generator is really more of an insurance policy. Maybe this microgrid is going to be really a financial driver for your facility, correct?
Correct, because really you're going to try to optimize and use obviously as much renewables as possible because the cost of generation is minimal, and you're going to try to avoid running your normal gensets which consume fuel. So that's a lot of things really which go on there, and that optimization, that intelligence in there is one of the keys factors. So let's break it down a little bit also in terms of the control architecture, kind of to show you how this modular concept works. So really on the primary side, that's very much the genset controllers still. So obviously we'll have to do typical genset things like stabilizing voltage and frequency. We offer a plug and play capability for adding different resources. We obviously share active and reactive power across these units, and want to mitigate circulating currents and other electrical issues. So that's kind of the primary control function there. On top of that comes the secondary control function, which really has to deal with, as we go in and out of island mode, more of a frequency and voltage restoration to always make sure that we use the assets we have to maintain voltage and frequency. That might involve a battery system or others to stabilize that. And the tertiary control, really the high-level control, that's where we optimize the use of all these technically and financially, and really manage the power flow intelligently to decide what asset to use.
Okay, so much like when we were talking about the battery energy storage systems in the last webinar, the closer we get down to the bottom, or the closer we get to the customer, in this case, the more revenue streams that we can really start to optimize.
Yeah, and that's really where the customer is going to be the key is on that, let's say, highest level, where there's really the intelligence to, and then that's what he worries about. So if we look at now as well the control architecture in terms of, again, visualizing the different gensets and the functions. So on the very bottom level, we have our resources for this purpose called that layer 0. That's your IOs to the generation and the storage assets, as well as renewables. The second layer is going to be the PLCs which come with these components. You'll have a PLC on a generator, you'll have a PLC in the battery, in the renewables. There'll be some kind of a controller which manages just individually that one asset. Then the layer 2 is really the microgrid controller. That's, or we can also call it the plant manager. That's where the intelligence sits. That's where really, all of this optimization happens, and I'll show you more about that later. And then on the highest level, that's where the operator is going to come in, as well as the service techs. That's where you'll have operator stations, portable units like phones and laptops, which can control and interface to the microgrid controller, and there may even be dedicated engineering servers or engineering interfaces on it. So this kind of just shows you the different levels which can exist in a microgrid situation and as far as controls go. And one thing also to add here, as you can see, kind of the double lines of the red and the blue, redundancy is a big thing as well, because you're going to depend on this for your power generation needs. And that's why controls redundancy, both in terms of communication channels, power, as well as the microgrid controller itself. Redundancy plays a key factor in here to make sure if one thing fails, you have redundant controls.
That's excellent. So like on layer 3, we can actually see, maybe as an engine manufacturer, maybe even digging down into the actual performance of the engine and maybe do some predictive maintenance to make sure that we have the most optimal uptime for the assets, right?
Correct. So really on the maintenance side, and that's why we show it separately here, to have an engineering and maintenance, let's say, server or access, and that allows service techs to really get a good feel of predictive maintenance, because we're going away from just very fixed schedules on doing things. We're going more into the adaptive maintenance by monitoring parameters on these units and then deciding when certain failures may happen, and then we replace parts. So yeah, that is a key factor. That obviously the goal is to really avoid any unplanned shutdown, and that's the goal here for having that.
Okay, so can we dig a little bit deeper into kind of the way the controls are set up now?
Yeah, so to highlight kind of the modular platform of this whole thing, I have here a slide which shows, in a way, a building kit. So on the left side, we talked a bit about the hardware. So obviously, we have a bunch of PCs, IPCs, industrial PCs. We have a bunch of PLCs as part of the system, displays, IOs, and network connections. So we'll have a lot of these hardware pieces which come in there depending on which layer you are in the controller. But importantly, on top of that is a software building kit, which can be adjusted based on the needs. So on the bottom is really the base genset controllers, storage controls, renewable controls, really the controls of the individual assets. Then we also control the power distribution functions, all the breakers. And on top of that is the microgrid control functions, which really are more of optimization, the intelligence, the analytics on how to dispatch these. And we try to really make this modular so that you can add or subtract functions as needed, because no microgrid is the same. So overall, we'll have an automation and control system which really can be customized and optimized to the customer needs and his microgrid.
Yeah, that makes really good sense, because you're right. No, there's not going to be any two applications that are really going to be identical, because we may have different, it may be the same company and the same type of warehouse, but it may be in different locations, and the ambient conditions may be completely different for one to another. So the more functionality and the more options that we can build into it, the more that we can customize it for the customer.
Yes, that's a key, customization in microgrids. So now let's talk a little bit more also about the operational modes, which we might see here in a microgrid. So we may have a grid parallel operational mode where we are tied to the grid. And in that case, the most basic function this controller has is really active power control. So obviously, we'll set a power set point, either to import or export power to the grid, or have neither, basically a zero load control. We'll also control reactive power. The KVAR is very much in the same way. We will still have an optimization if we have renewables in there, basically to reduce the use of gensets and the grid to produce as much power as we can through the renewables and avoid running the gensets or importing power from the utility. We're going to try and optimize the load factor and running hours of the gensets. So if they run, we try to run them at an optimal load factor. And importantly, if there's a battery storage there, we also want to control the state of charge of the battery, kind of to really keep it in an optimum range for the longevity of the battery, and also for it to, for example, be available to be charged from renewables or discharge power if we don't have them.
So it's, I see one of the ones that really is important for us as genset guys is that we're really optimizing the run hours of the genset. So that probably means that we can maybe do multiple generators of different kW on the same plant, maybe even the run hours across those engines. And then, if engine 1 needs to run during different parts of the day and engine 2 can run in different parts of the day, we can really spread those run hours out and extend the overhaul life on those engines quite a bit, right?
Yeah, that's right. And as you will show us actually later, it can really make sense to use gensets of different sizes to optimize the load factor. Because, we don't want to run a genset at 20 or 30% load if we can. We want to run it at a high load factor where it runs the most optimum in terms of fuel efficiency and also in terms of maintenance. So
absolutely.
So apart from the grid parallel mode, many microgrids run in island mode as well, and maybe exclusively in island mode. Maybe they're disconnected from the grid, as we kind of see here in this graphic. That is just a representation of a mine site, a remote mine site, which will have a microgrid. So in island mode, there will be some additional functions on top of what we just talked about. You typically would want to have a BESS, or battery energy storage system, to really improve the power quality by supporting the generators during transient load changes, especially if they're gas generators, which don't load up as quick as a diesel. Then it's great to have a battery which really smooths that transient and basically keeps power quality where it should be. Also, since we don't have a grid here where we could export excess renewable power, we'll want to have the battery energy storage system available to take that from the solar, from the wind, in case we don't have enough load at site, because we don't obviously want to curtail the renewable resources. We rather want to store the energy in the battery. And that's one of the key focuses in the intelligence here, is to try to avoid that in an island mode.
Yeah, as we'll see later on in the presentation, how important really using that battery to manage the transients on the gas engines in island mode really is important.
Yeah, absolutely. So now let's jump into the actual microgrid controller, and I'm going to walk through a couple slides here which show some screenshots of a microgrid controller which we use at MTU. And the first is really an overview of the system. So it really is quite neat. We have an overview of the different resources. In this case, we have a load, we have a genset, we have a battery, and we have some solar. So in this, we can see really just graphically what resources are producing power, what are consuming power. In this case, the load is taking on power. The majority of that comes from the solar, as we can see by the 3 green arrows, and a little bit of it comes through the battery just to top it off, and the genset is not running. This is kind of the ideal scenario where the solar is powering the complete facility. So you'll want to have a nice, graphical overview where you can immediately see what resources are operating and at what loads, as well as some basic performance history. As you can see, how much did each of these assets run yesterday, maybe over the last 30 days, and so forth, as well as maybe any alarms or other things which are immediately important. Then the next part is the capacity management. Here we see an overview of really kind of a day chart of how these different assets are being used. So you'll see in the green, that's the battery. In the yellow, that's kind of throughout the day, the amount of solar power which is being produced. Then there's the load in black, and then blue, that's the genset. So here you can really see how each of these assets performed over, let's say, the last day. And we can also see in this case that, let's say, throughout the day, the genset was not running, as we had a lot of power coming in from the solar. So, we optimized the genset starts by not running it throughout the day and then only running it in the night, as we don't have any solar, and then we can also charge the battery a bit through that.
So you can see so you can see when the battery is under, when we're below the line there, so we're using maybe some of the different assets that are available in the area to charge the battery, the renewables, instead of the grid or the engines, right?
Yeah, this is basically where we are not grid tied, so we're going to use the solar as much as we can to charge the battery through the day, have the genset off, maybe even store some additional energy in the battery, and then in the night we can use that and run the genset as needed, but not turning on and off the genset all the time. So this is kind of a neat graphical representation of how a day could look like. On the next slide, we want to focus specifically on the genset. So this just shows a time period when actually the genset was required to run. Let's say there was no renewable power or the battery was discharged. So in this case, we have two gensets, and you could see that the first genset is basically started up as the load comes up, and then second genset is later turned on as we need more power. The power which is needed is the green zigzag line there, and the power which is available from the gensets, the maximum power would be the blue. So for a certain number of hours, we're going to run both gensets, and then as the load drops, then we shut off one and then just keep the other one running for the rest of the time. So we kind of
this is really a great representation. Yep, this is a really great representation. So you can see the percentage of the capacity of the generator at the same time and the duration that it's run. So it really shows how we're really trying to keep that generator as highly loaded as possible, and when we kind of transition from one to the other.
Exactly. So that's the intelligence where you shut off one to always ensure that optimum load factor. And I mean, certainly you could also pre-program generator start times kind of to make sure that the generator is online when we might expect the need, so we don't have to wait for it to start up. And there's a bunch of intelligence you can do to try to optimize and find out when you should use the gensets and how many of the gensets you use. Yeah, absolutely. So then let's look a little bit at the solar aspect. So this highlights just one issue which we may have, and that's curtailment. So what does that mean? So basically we have see in the curve the power production of the solar. Then the load is the line above that. And if for whatever reason we cannot take the power which is generated from the solar, and we can't export it to the grid as we have in this case, then if the battery is fully charged, we have no other option but to curtail and basically shut off a certain amount of the solar, which we try to avoid because that's in essence wasting free energy. So that's kind of what you see here, that break-in, where now suddenly the total capacity in the system to take that power which is generated drops below the generation of the solar, and we'll have to curtail it. And that's what we really try to avoid. So how do we do that? We try to always maintain an optimum charge in the battery, where if we expect a lot of solar to produce, let's say during the peak hours during the day, we'll keep the battery at a little bit of a lower charge so that in case we don't use it in the building, then we can store it in the battery. So that's really also predictive intelligence where, let's say, weather data becomes relevant, because we'll be able to input weather data here, and if we expect, let's say, the afternoon to be really sunny, maybe we'll draw down the battery, shut off a generator, draw down the battery, because we know we'll have excess solar in the afternoon, and then we'll store it. So there's quite a few neat functions as well if you implement things like weather forecasts, and I guess hopefully they'll be accurate.
That gets really exciting when you get onto bigger facilities and you get in maybe where you're where you really can take into consideration maybe larger solar arrays, and there's really a lot of functionality that can be done, pairing those batteries with the solar really to optimize it with the controls, and you really see how important the control is here.
Yeah, absolutely. And it's a financial asset, as I said, you want to store the free energy, don't use the generator. So that's where it all becomes a financial tool. Now let's look a little bit about on the battery as well. So the battery has, quite a few functions which I guess are good to monitor. Obviously, you have an overview of all the parameters. You monitor the state of charge of the battery, which basically means how much charge does the battery have at any time. You want to avoid undesirable state of charges as well. For example, having a deeply discharged, you don't want that. You don't want the battery to be at 0% charge for a long time. You rather want to charge it up a bit because it reduces the life cycle of the battery cells. In addition, we always want to try to use fully utilize the battery capacity. So if we expect, for example, that inrush of solar power, we'll draw down the battery and then charge it with that. And one aspect, and we get that a lot, is also thermal monitoring, because we hear these stories about cars or other electric, let's say battery vehicles, etc., which have had some thermal issues, let's just say. And the battery energy storage system, which we have, basically monitors the thermal aspect of well. Obviously, thermals are dependent a lot on how much is being charged and discharged. As the inverter runs, it produces heat, but also the ambient conditions, because we'll have an HVAC system and we have to design that properly for the battery and the site. So as to avoid
that's really something that's been
thermal incidents. Yeah.
Yeah, that's something that really has tracked all the way through all of our presentations, that, ambient conditions are really an important factor when you're talking about sizing and designing a microgrid, whether it's, just a standalone generator or all these different assets together. The more ambient information you have when you start the project, the better you're going to be able to design it to meet the customer's needs.
Absolutely. Thermal aspects and controlling those on a battery are very important. So yeah, that's sort of the time we have to go through the Microgrid Controller and show you some functions. But we do also want to touch a little bit on the simulation tool, which we use to basically model the right solution for the right application. So I do assume, and you've done quite a few of these, that it's a little bit more complex than maybe your typical genset sizing tool, which you use.
Yeah, I would definitely say that's correct. We have the standard, the PS Spec sizing tool that's located on our website. But you're right, this is really a big leap forward from that, because now we're really talking about all these different financial considerations that we're rolling into it, and all these different, it's the grid, it's all these different distributed generation assets that we've got. So really, we really like to put our money where our mouth is. So MTU has developed a validation center where we can do dynamic modeling for microgrids. We can simulate wind and solar, and we actually have solar panels installed on the roof of the validation center, along with a battery energy storage system, diesel standby, and cogeneration, along with a grid tie, all at this single site at our headquarters in Friedrichshafen. And we can really simulate real-world applications for customers. So they can come to us with applications, and we can really come to them with a solution, which is really our goal at the end of the day, is to sell really well-designed and well-engineered energy solutions to our customers and partners. And this really has been this is going to be a great tool to help us do that as we go forward.
Mm-hmm. So yeah, I mean, that's obviously, you want to validate what you have, but also I think there's also software ways to do it. Maybe if you can't necessarily model it in the actual validation system. So maybe you could walk me through let's say the modeling process for a typical microgrid.
Sure. So we really have, there's two steps to this really. So it's the initial, it's the high level. Are we wasting our time? Is there even a project here at the end of the day? And then once we establish that, then we can get into some of the financial optimization part of it. So really what we try to do, as always, we want to gather as much information about the project as early on as we can, what the load profile looks like, both electric and thermal, because this is going to be some kind of a distributed generation asset. And in this case that we're going to talk about today, there's going to be cogeneration. So we also have to understand what the CapEx is. How much is it going to cost to purchase all these different assets? So we program all of this into the system, and it's going to help us design and come up with the solution for the customer.
Yeah, absolutely. And the financial aspect plays a big role of it. So I think you've done a couple of these, and maybe would you walk us through an example, an actual project which was modeled for a microgrid application?
Sure. So this is an off-grid greenhouse application in the Southwest, and it became a microgrid application because there was really limited three-phase power available for the actual processing portion. So we have got three-phase for the office, but the site is going to need so much more than that. It's over 160,000 square feet. It's kind of a clear glass European design. So being located in the Southwest, the cooling is really going to be the biggest concern that we're going to be handling and really worried about in this particular application. So we were able to get a lot of that early information from the customer as we started to make our models, as you'll see kind of as we go forward.
Yeah, so I guess it all starts with the load data, as you mentioned. So what did we get here from the customer?
So really, because in this case, it's a microgrid, limited or no three-phase power, our energy system has to really be the utility for this customer. So based on the information that they gave us, they gave us, as you can see, there's some maybe different load on an hour of a day for summer loads than there are to the winter loads. But after we modeled all of that over a 8,760 hour a year, it came out that we had to support over 13 million kilowatt hours for a calendar year. So now that we know how much power is required, we're going to be able to start designing what the power plant's going to look like.
Yeah, and I'm sure they gave us the annual data both on the electrical and thermal loads too, because as you mentioned, it's a CHP application as well, so there's thermal loads as well.
So this allows us to really also, we're talking about optimization. So with a natural gas generator set, ideally, if we want to optimize it, we want to capture as much of that heat as possible. So you can see on the right-hand side, we have the thermal loads, and on the left-hand side, we have the electrical loads. And you can see they kind of match up to each other. So the output of the engines is really going to match up the thermal output of the engines during the time of the year. And that's going to allow us really to match up different sized engines at different times of the year and even different times of the day to the loads as we run them.
Yeah, and I'm sure looking at this is thousands, if not millions, of little data points. So what then happened when you put that into the tool? What came out as a solution?
So what came out in this particular application was two of our 8V4000 natural gas engines, which are about 762 kW each, and two of our 16Vs, which are about 1,500 kW apiece, plus an MTU battery pack, which is about 700 kVA. So this is going to really allow us to run this site with the best optimization as possible. And you can even see on the right-hand side what percent of the year that each of these engines are going to be called upon and dispatched. In this particular software model, it doesn't have the ability to levelize the hours on the engines as we run this model, but we're going to know as we run this and put it into the microgrid system that the microgrid is actually going to levelize the engine runtime. So we're not going to have one engine at 22% and another at 3%. We're going to be able to really even those out across all of them.
Mm-hmm. Yeah, that's interesting. And so, like you said, you're going to optimize the run hours. So maybe if we dig a little deeper into the natural gas gensets and how they're used, what does this overview show us of all those 4 units which are proposed here?
So one of the things as we look at on a cogeneration project, and especially one maybe now even a microgrid like this, where the primary power source is going to be natural gas fuel, if you look at the 10-year life cycle cost of this plant, like 75 to 80% of the total cost of this plant is going to be the fuel used to run the engines. So we can even see as we dive deeper into the modeling program how much fuel each of these engines is going to consume on a yearly basis, the number of starts, that goes into the predictive maintenance like we talked about earlier. And, and the capacity factor, once again, like we talked about with the different dispatchable assets, we really can get in and dig into the details of how these engines are going to perform and what the true cost of operating this plant for the customer is going to be, which is really important for the end user because, we want to make sure that we are at or below the cost that we have discussed with the customer, and we want to try to generate electricity at a lower cost than they could purchase from the grid.
Yeah, that's going to be a key output to give them kind of a number at the end of the day. So if we now take this and look at it more graphically to see how often and how long we use all those assets.
This graph, if we all grew up in the 80s, this graph kind of looks like a chia pet with all the lines and everything on it and the different colors. But what this really is, it's the time of year when the different generation assets are being deployed and for how long and for what percentage. We're going to dig deeper into this as we go, but this really is kind of the very first overview of the entire year. You can see below when the battery is being recharged by the different assets. You can see up top when all 4 generators are running, and you can see that when the generation assets are recharging and discharging the battery. So over the full year, we're really getting this is really the full view of the power plant.
So you can really see some of the gensets are running more base load, and then the others are running only parts of the year as needed. And this is obviously a lot of lines, a lot of color here, but I think when we look at it also on a weekly basis, it also can show us some interesting things.
Yep. So what you can see here, this is we kind of took a snapshot of the week, so you can see a full day, and then once again, like you talked about, there's really just going to be a couple generators that are going to operate base load all the time, and that's that kind of that 762 kW generator. And then you can see as the day comes in, we're going to charge up some of these batteries, and the power is going to go up and up and up a little bit. And you can see at different parts of the day that when all 4 generation assets are being used. So you can really see that we're really getting into the details about how this plant is going to run, and it really, really gives us a really good snapshot and a lot of information that we can share with the customer. And on the next slide, you can see we're really going to get down into the 24-hour day and really show how the system is going to perform. And it gets kind of really, as you're a generation guy, you really get excited to kind of see how this thing really is working with the grid and with the other different assets that are part of it. And here on the graph on the left, you can see that the battery is being charged as the load changes. The battery is being discharged as the load and generation asset is changing from one to another. So this goes back to one of the first things we talked about, is that for battery energy storage systems are really required with natural gas generators to make sure that we can transition those loads from one engine to the other. And that's really displayed here on this like 24-hour a day graph. It's really kind of interesting.
Yeah, you can see basically one unit is sort of used like a peaker during the peak hours. So if we look at that, like for example, also taking that peaker there, if we look at it from basically the run hours over the year, I guess that one unit probably doesn't run that much.
Yep, and this is a really, once again, we're demonstrating to the customer, we're demonstrating to ourselves, how many hours in the year each of these different assets is running. So you can see the brown 763 kW unit is really used, like you nailed it on the last slide, it's really being used as a peaker. So once we get into the microgrid control setup, we'll be able to make sure we levelize the run hours between that brown unit and the purple unit that's all the way down at the bottom, to make sure that we're not overstressing and moving that overhaul, that big maintenance out as far out as possible, and really levelizing the run hours across the engines.
And then on the purple on the bottom, as you said, that's basically the same unit, the same 760 kW unit as the brown on the top. And we can basically see that pretty much that unit is going to run continuously throughout the year. And at some portions, I guess, during the night especially, that's maybe the only unit which runs. That's
yes,
why it
absolutely.
shows 4,000, 8,000 hours. There's no other genset running, and that's basically half of the year in terms of annual run hours. We just need one genset to support the load. But then on other days, like in winter or so, when we need also more thermals, we'll have all 4 of them running on those peak hours.
Yep.
Yeah, so I mean, obviously there's a lot of kind of graphs here to show this, but maybe as the last slide here on this tool, I do want to also touch a little bit on availability. How does that play in terms of modeling this, Tom?
Well, that really is key, because once again, like we talked about, we're off-grid. There's no 3-phase power. There's no utility to fall back on. So we have to make sure that we make this information allows us to give information to the customer too, to make intelligent decisions about what the power plant is going to look like. And in this case, we're really going to show that how many hours a year, if one of the 2 engine models has a failure or is down for maintenance, what kind of risk is present to the customer if that engine isn't running. So once again, this simulation tool really allows us to, maybe the customer at that point can't abide by that percentage of risk, and they add a second engine in it, like an N+1 arrangement, to make sure that they don't that they are never without power, or maybe there's a way that they can manage it, and as long as they're aware of it, they can make those intelligent decisions.
Yeah, I guess that helps them, first of all, to decide, when to do maintenance, and also if they are really focused on availability, then they can add another unit in this tool, and immediately you can see the shift of numbers, maybe going from a 7% probability that at any given time there's an outage to maybe, a much lower probability, and then you can decide if that's financially worthwhile. That's pretty neat, I think.
Absolutely. Yes, absolutely.
I think that's one of the key factors of this. So that's what we want to talk about here on the simulation side. So let's just recap it, Tom, if you could, kind of what we went through today.
Sure. So, some of the trends that we see in intelligent controls is that historically, generation has followed the load. Big power plants, coal, natural gas, nuclear, that are just pumping out power continuously, and creation and consumption is happening in real time, and it's always there to meet it, and there's really no variability. It's a constant creation of power. So in the future, really is now, because these systems and units are getting installed all over the world, but with a greater penetration of renewables and the variable creation of power that comes with those renewables, we really have to do a better job of optimizing the assets. And that's really where the controls are going to come in, where we can optimize the grid, the load, and the distributed generation assets, really to drive down the cost and increase power security.
Yeah, because really now you as the customer have the intelligence. You don't just depend on the utility. I'm going to provide you power, and this is the price you have to pay, and you pay it if you want it or not. Like, for example, on that event which happened in Texas, I know because I'm based in Texas, in August, where basically they were charging outrageous amounts for a couple hours of the day. If you had a microgrid, you could just go offline and use your own assets. So that's really where you have more power now than previously. So I think really the takeaway is that if you have a microgrid, it offers you a solution to cover a local energy demand in the most economical way, considering really the needs of your site here and the local boundary conditions, if you have a grid or not. And that energy demand can really be electrical power. It can be also combined with thermal demands. And we combine distributed energy resources, energy storage, all with an intelligent control system, which may or may not connect us to the grid. So really, we have value streams which are available to us through using renewables, avoiding those peak charges, and in essence, we really have a smart grid where we choose which asset to run, which is best. And we can call this all basically a hybrid solution, as we combine genset, energy storage, and renewables. So it's really a hybrid, not only relying on one technology. Well, great. I guess I think now it's time for a couple questions. We do still have a few minutes here.
Thank you, Christian and Tom, for that great presentation. Now our presenters will answer questions from the audience. Questions that we don't get to today will be posted online at www.csemag.com with the archived version of the webcast. Moderating the Q&A session today is Brian Ponstein. Brian is Regional Sales Engineer at MTU On-Site Energy. He is responsible for sales engineering for half the United States and all of Canada. He has a bachelor's degree in heavy equipment service engineering and a master's degree in business administration from Ferris State University. Brian brings more than 11 years of experience to the company. Brian, welcome. And we're ready to start the Q&A.
Thanks, Jack. Christian and Tom, there's been a lot of questions coming in about the size of these systems. I mean, you've talked about some fairly big ones, but I mean, is the size a function of feasibility, or can you kind of really touch home on that topic to really address whether there's a size related to feasibility of these microgrids, or if there's other parameters that really drive the feasibility standpoint?
Well, size, really at the end of the day, it's the cost of the equipment, and there's always cost savings in scope. So, that just is historical. The bigger you build something, sometimes the less expensive it is to build per square foot or per kilowatt. So really, size is less important as the different assets you're going to tie together. I mean, when you really get into the nuts and bolts of it, the controller doesn't care if it's a 1,000 megawatt combined cycle turbine or a 10 kW solar panel. What we're looking at is the interplay between all of the different assets to make sure they operate efficiently.
Thanks, Tom. The other question that I want to get at is, why are batteries needed in pairing with gas engines, and really kind of relating that to the types of transient load steps that we're able to handle? I think you're going to kind of answer both of those in there.
Yes, so absolutely. So a gas genset on average can probably do anywhere between, let's say, 10 to 30% load steps, not like a diesel, which can do 100%. Now, there are certain gas standby units which could do more, but really for most of these applications, as we're going to run them continuously, we can't use a gas standby. So we're going to use a continuous rated gas genset, which can do anywhere between 30 to 10% load steps. So obviously we could oversize, add more gensets in to bring it up to whatever we need, but the battery is going to be much more financially feasible. So we're going to add a battery. If there's let's say a 1 megawatt load step and we have a 1 megawatt battery, then that 1 megawatt goes onto the battery, and then the battery instantaneously absorbs it, and then the gensets ramp up according to what they can, and then transfer the power, or basically the load, from the battery to the genset. So basically the battery is could also be like a spinning reserve or other things. So it really is needed to take those transient load steps, which allow us to use gas gensets and don't go to, let's say, diesel gensets, which are more expensive in terms of operational costs and environmental issues and so forth. So that's one of the neat functions, of course, in addition to being able to store renewable energy. So it kind of has two functions, the battery. But yeah, definitely a battery is going to be cheaper at the end of the day than adding additional generators to handle loads.
And I'm just going to take one quick question before we end out. These systems, are they really, in previous webinars we talked about it, but I think it's good to reiterate it again. Are we looking at behind the meter applications only here, or is this both sides of the meter that we're really looking at for these microgrids and looking at these systems?
Tom?
Our focus is always, our focus normally is going to be on the behind the meter applications. That we feel that that's where we can add the most value with the different types of assets that we have between the gas engines, the diesel engines, and the batteries. But they're, as a project and microgrids as a whole, you can see there's utility grade and utility scale microgrids out there right now. So our focus as a company really is behind the meter, but microgrids as a whole, you can remove whole sections of the grid and power it, or whole neighborhoods in a city and put them onto a microgrid. It's really what risks you're willing to take and what parts of the facilities you're able to separate.
Yeah, I agree, Tom. It's really those behind the meter applications for large users, that could be, let's say, an army base or a large industrial user or a greenhouse, as you say, a large center of demand, and then you remove that portion, and then there's a lot of value in doing that. I think that's really the trend we see right now in microgrids, is that.
Thanks, guys. There's a whole lot more questions that we've got to answer here after this webinar. We just don't have enough time to get to all of them. Jack, I'm going to pass it back to you.
Thank you. Thanks for the great questions, and thanks for the excellent answers. Thanks again to our great speakers, Christian Mueller and Tom Drake, for sharing their time and expertise, and Brian Ponstein for moderating the Q&A. I'd also like to extend special thanks to our sponsor, MTU On-Site Energy, for sponsoring today's event. Now that we're just about done, we want to hear how we did. Exit survey will pop up on your screen as soon as the webcast ends. Please take a moment to complete it because we use this information to improve our webcasts. Finally, on behalf of Consulting Specifying Engineer and CFE Media, I'd like to thank you for attending. This concludes our webcast. Thank you and goodbye.